We are live. All right. Greetings, sailors. Today we're gonna have a really long stream, and we're gonna do a lot of stuff. Now, I assume that today we're gonna get so many things done, many little things done, that basically the physics simulation, that is our piece of software that we've been working on for the past few streams. In this stream, it will start to look like a game. Okay, that's what's going to happen. So yeah, let's see if we can do all these things. So let's start off with with finishing the tasks that I had in the previous stream. But before then, actually, let's look at what are we actually working on. What is this strange whaling game? This is, well, it's not a game. It's basically a physics simulation for now. And so this was the first stream. The result of the first stream, we have water and different weights, and you can see the water slows down the 8 kilogram object as opposed to this. And depending on how heavy each object is, so basically we implemented buoyancy. That's what I'm trying to say. Then we had this kind of, distribution of weights. You see the heavier one is slowly moving up. And then in the previous stream, we implemented waves. So you can see these are, there's two things happening here. One is that we're generating a sine wave. Well, actually, multiple things that are happening. We're generating a sine wave to create waves. And because just a normal sine wave would be too harmonic, all of these things would move in very predictable ways. That doesn't necessarily look like the sea. I might have to actually modify some parts of this, because whenever there's this, whenever we have a falling wave here, it means these items are being sucked down, forced downwards. And whenever we have these lines rising above the midpoint, that's when the force is acting on these objects, upwards. Okay, so these things are being moved up and down depending on the kind of wave that the sea is generating, this body of water. And there's also small variations within the sine wave. You can see it is wobbly on the macro scale, and even the smaller waves themselves have a slight wobble to them. And this is because, now that I think about it, this might be a bit too chaotic, but with playtesting, we'll find out what are the actual parameters for the waves, how frequent they should be, how big they should be, should they even have downward force or stuff like that. Maybe I should maybe it shouldn't even be shifted upwards. But maybe we should just eliminate any downward force. Okay, so stuff like that. We'll find that out through playtesting, because with just this, there's nothing to play with except the physics system. And the idea here is these are crates basically, and we're going to have a small boat, and there's going to be a player in the boat, and he can throw spears at a whale. We're not going to implement a rope or anything of that sort. Actually, today's plan can be modified a bit after estimation. But yeah, so we're going to turn this into sort of a game, okay? So yeah, today's plan. This is the task from the previous day. This will take me 30 minutes. What this is going to do basically is, so if you look at the situation here, yes, these things are moving up and down, but they're not very realistic in terms of they don't look like they're crates in the sea. They look like a physics simulation. I think what would add realism to this is if I added some random amount of rotation to these crates. Okay, so we move them backwards and forwards because that's what happens in the sea, right? So we'll this is what local rotation noise does. It basically, based on some kind of data that we can gather from this, I'll just create a random rotation vector and apply that rotation to things that are under the wave at that point. So yeah. Yeah, this is a bit too chaotic, now that I think about it. So like the waves should move much more slowly. And I think their amplitude is about correct. Maybe we'll need to eliminate the lower, stuff going low. But this is a bit too fast. So actually, before I get into today's plan, let me make a quick fix here. So I have the water object here. This has wave shift speed. Okay. So we'll make this slower. So if we do it like this, okay, this looks nicer. This looks kind of nicer. I might actually slow this down a bit. So the second. Yeah, let's make that 17. Okay, let's not play around too much with the parameters. But yeah, local rotation noise, just rotate the things. Make a boat. I think this will take like 30 minutes. Polygon. Yeah, a character with movement, and that might be a bit too much, but what we should do, I think, is add camera controls. This should also take 30 minutes. So like scrolling around using the mouse, basically. Make a character with movement code. I'm not sure about that yet, but if I want to steer the boat forwards and backwards, yeah, maybe we'll just make the boat, and the steering and the character is kind of hard. Let's make a whale that will have that swims. I think this is going to take like 3 hours. And in order to throw spear at a whale, we need to have a character with movement. This is going to take about 2 hours. And steering the boat. Forwards and backwards. I think that's going to be like an hour of work. So then we make a spear object. It's probably going to be like 30 minutes. And then throwing a spear at the whale is probably going to take an hour of work. And killing the whale is going to be 1 more hour. Maybe like bonus add blood particles. It's probably going to take 30 minutes or something. So if we sum all these up, this is going to be 5 hours, 6, 7. Okay, so 5, 6, 7, 8, 9, and 10. So in 10 hours, we should be able to finish all of this. And then 10 and a half for this. But let's see. What I'm going to do actually is save this file. So I'm just going to copy this. I'm gonna paste them here. And the actual, so these are my estimates, right? And we're gonna say however long that takes us. We're gonna basically say how long that took us, okay? So this is the estimate, and this is gonna be how much time it takes us to actually do that stuff. Okay, so yeah, let's get to it. So let's add local rotation noise to this stuff. So here we go. Let's get some music, actually. Let's get some sea shanties. Pirate music. Okay, great. So let's get to it. Local rotation noise. So what we're doing here is, yeah, this is boring. Okay, let's do rotation. Yeah, we can do that easily. So let me do it like this. Yeah, let's close this. So so here's what I'm thinking. We calculate rotation based on the arrangement of these guys. So basically, the way we apply force to this stuff is let me see. Right, so so we apply the force here. So we calculate the force based on the volume, the rough volume, and then we apply the wave force by getting the interpolated wave force and point at the center point. Okay, so now we apply the angular damping, that's correct. because we don't, so if I grab this object, you see it rotating, right? But if I put it underwater, it should not be rotating as fast, okay? So if I throw the object like this, you can see underwater, it's slowing down, okay? It's slowing down the rotation. Okay, so now what we want to do is here apply rotation force, apply random rotation based on wave, okay? And well, we do call get interpolated wave force at point. Once we do call that. This could basically return, yeah, okay. And rotation. So this could return wave force and rotation. So force and rotation, force equals wave force, wave rotation. It could return two values because we can calculate two things at once. And yeah, okay. So we'll do obj body apply torque here. Right, so we have force, we'll do for now it's gonna be 0, and gonna do, yeah, so torque. Well, this is counter torque, right? So we're applying angular damping, and so should we dampen? So like, should we dampen before we apply the rotation, or should we dampen afterwards? No, because we should dampen the movement and then apply a counter force. But the next frame we're going to be damping it anyway, so it doesn't actually matter. Maybe. We apply the torque. No, not apply. We add the torque and yeah, this looks okay. So Apply wave force and rotation. Right. So now all we got to do is implement the actual function. We'll expand this function to have that. So we have interpolated wave force at point. Right. So we have this. So we'll do local force is equal to that. And torque is going to be equal to something else. Okay, so let's do local F1 is this. Local F2 is this. Then we interpolate F1 to F2 with this interpolant value. So what this is doing is it's returning based on, but there's these gaps between these points, right? And the lines need to appear there, right? So actually, now that I think about it, why does the sample rate need to be that high? It doesn't. Well, if we have like performance issues, maybe I can lower the sample rate later and play with the parameters. But anyway, so this is basically how much between these 2 points the point is. And the torque is basically gonna be, let's do smooth linear interpolation, maybe. Of this. And I guess we can do something like this. Let's play around with this, okay? So, yeah. What else? I might have to multiply this by something or whatever, but let's try it. Equal amount, right? Oh yeah, you can't really do this. Yeah. Okay. So slurp needs to be something else. So we'll do function. Oh, actually, I can just apply slurp to. So it gets the smooth amount and then does a lerp on that. Right. So I can just do this. Yeah, you can't do this. Okay, so, ooh, look at the rotation. Can we have a smoother slurp? So let's see. Smoothing functions. I want to see graphs. I want it to be like a sigmoid. Well, our our smoothing function is like a sigmoid, but I want it to be more sigmoidal, I guess. No, so I want this interval to be like smaller, squished down. Let me actually do Desmos calculator. That's the one, right? Yeah. So let me just actually put the polynomial in there. So this is y equals x squared times 3 minus 2 times x, 2x. Right. So what we're looking at is this. Phew. Right. So if we make this 3 cubed, no, not 32. How about 4? Wait. Let me see what this looks like if I increase 6, 8. Oh, let's do 5, 7, 9. Yeah, no, I don't like that. Right. So 1 minus this, 2, 3, 4. Ah, I see. So it goes up higher. But actually we want this to be 3 because we want it to be contained in this singular little square. What if we put 3x here? Right, it just falls. Ah, okay. Times 2, 3. Alright. And I can maybe do 6 minus? No. So 1.5 minus this. 2 minus this. 3. Yeah, no. So hermit function. So what I'm trying to do is basically have something like this function, but what I want is for this to be flatter and for for it to be less linear. So I want to basically squish this down. Okay, I want it to be long. I want it to be closer to 0 for longer, and then suddenly jump up to 1 and closer to 1. Because what I'm trying to achieve is not slight, slow rotations. I'm trying to achieve quick rotation to the left, or maybe quick rotation to the right, because that's how I imagine the water applies force, applies torque to a bunch of objects. So basically it just whips it to the left, or maybe whips it to the right really quickly, and it just bobs back and forth, something like that. So that's what I'm trying to achieve. So I don't know the exact like the kind of function that I can use to modify this to sort of do that. There was this other one which is in simplex, not simplex, Perlin noise smoothing function. Brave Search sucks. Jeez. There we go, smooth step. This is already what we're using. Current pronunciation replace smooth with the following one. Right, so this is the one that we want. So we want SSLerp, function math SSLerp. Actually, we'll do smooth math, smooth. So we'll return, so we have t return 6 times t to the power of 5 minus 15 times t to the power of 4 plus 10 times t to the power of 3. Like if we put this stuff in here, y equals this. Yeah, this is what I was kind of looking for, you know? Sort of what I was looking for. I mean, closer. It's closer to what I'm looking for, but I want it to be squished down even more, you know? Smoothing functions by graph. I want to look for graphs of these functions. Oh, whatever. Okay. I guess we'll have to... Kernel smoother. Let's see.
Wanna know why Roger is so jolly?
Oh, how about what are those called? Curve generator. There's this other thing. No, what are those called? Like you can make splines or... Beziers, yeah. Yes, okay, okay. So this is what I'm looking for. This is what I'm looking for. Yep. Yeah, exactly. So, how do I generate this cubic Bezier? Okay, so cubic So this is the formula. So we have 4 control points. I remember there's some So quadratic curve is the path traced by the function bt given the points p0, p1, and p2, where 1 minus t plus t times p1 plus where t is between 0 and 1. So 1 minus t squared times p0 plus 2 times 1 minus t times t p1 So this is P0, this is P1, and this is P2. So from P0 to P1, and from P1 to P2, the curve starts at P0, going toward P1, and arrives at P3. Ah, okay, so here is, this is P0, this is P2, this is, sorry, P0, P1, P2. contain a cusp. Ah. Yeah, this is taking longer than 30 minutes. Okay, so this is taken straight from Wikipedia. Even the italics are exactly the same. Okay, now this completely makes sense. Yep, absolutely. So, as you're moving across those lines, and then you're interpolating between those two based on t as well. Yeah. It's like this one image just made everything make sense. Great. So this one animation. So what you're doing here is you're doing a quadratic. Okay, so let's see what's up. So you're getting the point at, you're getting the location at which each point lies, depending on t. Then you are interpolating the first two. So you're interpolating the one between P0, P1 and P1, P2 to make a line. Not interpolating, but yeah, basically. You're making a line between those. Then you're making a line between P2, P3 and P1, P2. And you're interpolating t in between those two. And that's... yeah. And then when you get that line, t, you're interpolating that according to t. Yeah. Okay, so I understand this, but just to save time, I would basically well, actually, I'll just take the formula and just implement it according to the formula. But I get it. If I were to do it myself, I would follow the visuals. Right. This is a dot product. So I get this part. Okay, so we have P1 and P2. Okay. So zero, one, two. So we have a line here and a line here. And if t is equal to like 0.2 or something, this is going to be 0.2 of the way there. This one here as well. And so P0, P1, P2. The curve itself is going to be like something like this. No, something like that. But yeah, we're not talking about that here. So 1 minus t2, 1 minus t, which is 0.8, plus t times p2. This is vector addition, I assume. Right? Because these points are points in space, right? So this guy. How does it approximate? How does cubic Bezier use like freaking 4 numbers only? Ah, no, it does not use 4 numbers. Okay, it uses 2 numbers. This is the first vector, this is the second vector. Okay, that's cool. Right. So naturally in our configuration we would have all these points, but P0 would always be 0, 0. And P4 would always be 1, 1. Okay. So we want something like this. Yeah. Anyway. Okay, that makes sense. Yeah, that makes sense. Right, so but you know, come to think of it, like, so this is t, this is 1 minus t, this is 1 minus t, this is t. Basically, if these lengths were 1, we would do something like this. P1 and P2. For a linear Bezier curve, it would be, actually let's start with just linear stuff. We like to keep it linear here. Anyway, simple. Ah, my bad. So that's the deal. What is wrong with this thing? All right. So if we have P0 and P1, a Bezier curve between them would look, imagine this is straight, right? So P0 times, so if T is equal to 0.2, it's gonna lay somewhere here. And so P0 dot, so 1 minus t, which is 0.8, plus P1 dot producted with 0.2. Right. So now why do they use a dot product here? How can you even do no, you can't do a dot product with freaking a scalar and a vector. Yeah, that's stupid. You do a dot product between two vectors and you get a scalar. Yeah. So really this is just a scalar multiplication of the vector. I understand. Kind of. So like, well, not completely though. So if we have P1, let's say it's 1, 1. Sorry, P0 is 1, 1. Well, actually, yeah. So this is 1, 1. And P1 is, let's say, 3, 2. Okay, so this is 1, 2, 3. This is 1, 2. Okay. Right. Bezier curve between those two would be this. Okay. So like at 0.5, so if t is equal to like 0.5, that would be the midpoint, right, between these two. So that would be, you know, between these, and so halfway between this and halfway between this. So it would be at, you know, this point. It's not drawn correctly, but whatever. So it would be at 1.52, okay? So, so we do vector times scalar plus vector times scalar, and we get back a vector, right? So the answer should be, so for this formula, the answer should be 1.5 and 2, right? So how do we get this? Let me see. So you multiply 1, 1 by 0.5, and you get back 0.5, 0.5, essentially. So that's the first part. Then this digital pad sucks because it keeps losing this. Keeps losing the touch. Anyway. The second one is going to give back what exactly? So if it's 2, 3, it's going to give back 0.5 and 1.5. So, sorry, 1 and 1.5. Come on, move. Oh my goodness. This thing sucks. Okay. Like maybe there's something wrong with this. It didn't actually used to do this. I have to basically almost touch this thing. Okay, this is so much better. Okay. So now it should, no, it's not doing anything. It's not doing anything. Okay, I'm gonna give this like 1 more minute and maybe, no, it's not working at all. Okay. What if I did enable pressure sensitivity? That does nothing. Did this thing just literally do nothing? Dude, I set the... Oh my god. Okay. So I want this and this and okay. And options. Oh, I customized it for this specifically. Okay. Now I get it. So yes, no more accidental strokes anymore, baby. Okay, so okay, so let me just delete this stuff. Now we're gonna draw much better. Okay. Okay, so we'll be getting basically, we would be getting, so the midpoint of the first thing, which is 0.5, 0.5, and the second thing we would be getting is the midpoint of the second point, which is 2, 3, which is 1.5. This is still crap. This is still really bad. So, and then you sum those up, I guess. So you get 1.5 and 2. Yeah. So that's what we get. This equals that. Okay, that makes sense. So now, gotta do it the other way around. Now we gotta do it for this guy. So you get the midpoint. No, it's not that simple. Well, you get the midpoint between these two, and you get the midpoint between these two. Not midpoint, but the point. Oh, so you get this vector, right? You subtract it, yeah. Okay, and then you multiply it by that much. There you get the vector. Then you get this vector. So then you have this, and you multiply it by that, you get this vector. And then you form a line between these two, and you get and you get that. So this is one of the points, so you would end up moving like this. Okay, so then I understand. Okay, so this makes sense now in its entirety. But this is only for quadratic. For cubic, you must expand it, I guess. For cubic, you would do this twice. This is wrong. How could it have... Oh no, P1 to Pn. Okay. Yeah. So a cubic one has two quadratic ones in there. Right? Yeah. Yeah, it does. Gibberish here for now, but find the point, interpolate, and find the other point. Yeah, so you make a vector between these 2 points. Okay. There. And then you grab that, and that's the point you want. That's great. But like, I kind of feel like instead of interpolating more and more, you could just use one formula like this. So to put this into our, so in order to make our final formula for this, we'll name this Nico's Bezier. No. Smoothing. Yeah, I'll just name it Nico, whatever. This is my Bezier function. Okay. So where was that thing? This one. Yeah. These are the points. Yeah, so let me... No, I don't want to copy that. I want to copy this. Whatever, okay. So I'll just put this here. So the way this is, let's see, so 0. Oh, I can't edit it, great. So this looks like 0.85. This is 0.85 and 5. And no, it was 0.05. Yeah, something like this. And then this guy looks something like this, basically. So basically something like that, yeah. Anyway, so let's use the... So these vectors are gonna be, let's see, So P0, let me do this here. P0 is going to be 0, 0, obviously. P1 is going to be 0.85, 0.05. P2 is going to be 0.2, 0. Actually, let's do 05.093. Yeah, to keep it symmetrical, you know. Something like that, yeah. So yeah, maybe we can save this for later, but yeah, save that for later. But let's keep it symmetrical. Okay, and then P4 is 1, 1. Okay, so now to calculate the Bézier curve here, we do right. So here's the formula: 1 minus t cubed times P0. This is going to be, yeah, so let's write this out completely, and then I'll simplify it. Okay, so that plus 3 times 1 minus t squared, so this is separate, times t times p1. Okay, plus 3 times 1 minus t squared times p2. Why is there no t there? I guess it cancels out in some way. And plus t cubed times p3. Why is there no mention of p4 here? So 1, 2, 3, 4. Oh no, it's 0, 1. Ah, I'm dumb. Okay, there we go. So yes. Yeah, so this is the final formula. So from here, we know that this guy, well, since P0 is 0, 0, so this is going to give us 0, 0. There's no way around this, so we have to put that in there. Okay. We go curve. Actually, let's do Bézier curve, and we'll do, so this is P1x, P1y, P2x, P2y. Okay. And we don't even need the curve, it's obvious that it's a Bézier. Right, so we do, so that's 0, 0. Okay. In any case, yeah. We can calculate this as well. Since P3 is always going to be this, so these are interchangeable. These can also be stuff like, so this is P1x, P1y, and for this guy is P2x, P2y. Right. This can be t cubed times p3 is going to be Also we know, yeah. So we know, like, yeah, this is dumb. So we need t here. Yeah. T cubed times p3, which is t cubed what the function has to return is the y-coordinate of the final vector. Okay. Yeah. So this is going to be... Oof. I don't think we can simplify this. Yeah, I'm not going to simplify that. So, yeah, we'll have 0, 0 plus t cubed. So this plus this simplifies to basically, so this entire thing can simplify to, well, no matter how much you multiply and change it, we only need the y value, right? So t cubed plus the y value of this plus the y value of this. So this is the simplified formula. So if you multiply actually, okay. Let's calculate all of this in terms of vectors. Then we'll do it. But I need to test this out somehow, right? So, can we get a generic Bezier curve function Lua? We just need this, right? So, but doesn't the x value matter? It should. Let me think back to this here. Okay, screw it, whatever. Let's do it this way. So, start off with 0, 0. Actually, we start off with t cubed, okay? It's gonna be t cubed. Oh, getting a call. Be right back. Yep, we're back. Right. Maybe I should turn off my phone forever and never turn it on. Ever. Right, so trying to approximate that. Right, where were we? Yeah, so local y is going to be equal to that as well. Then we're going to do, let's see. So this. Then we're doing, right, p1 x, x equals x plus, let's see, p1x times t, times 3 times, well, let's do it normally. So 3 times 1 minus t squared, okay, then this times t times p1x, okay, y is gonna be y plus the same thing but with p1y, so that's this part. Then we go, the next part is x equals x plus 3 times 1 minus t squared. We'll optimize this later. T, oh no t, just p2x. And same goes for y. Then we return x and y. Okay. So that's it, I guess. So if I plug in these numbers, I should get a really nice curve. What I want to do is test this out in a separate project. It's gonna be Euler. Let's make a temp in Lua, and we'll do, okay, right, and we'll do for t equals 0 until 1, 0.01 do, and we'll draw this thing. Circle. I mean, I could use GraphLove for this, but yeah, whatever. Fill, oops. So, Love Graphics, clear, black. Let's do black on white, okay. And then we'll do graphics and color. And we'll do something like this. So GW is get width. Okay, I'll set that here. Okay, then we'll do this. Okay, so x, y, and radius. Let's do r equal to 3. So this is gonna be math Bezier t p1x is 0.85. This is 0.05. Then we have 0.05, 0.85. This is gonna be, so local relative x and relative y are gonna be this, and this is gonna be rel x times game width, rel y times game height. Actually, we'll do, let's see, w is game width times this, height is game height times this. So we can have some margin. Okay, width and height. And r is for radius. And this has to take place in, this has to be game width times 0.05 plus this. And this has to be game height times 0.05 plus this. So if we run this, we should get a Bezier curve that is similar to this. What do you mean? Okay, circle. Yeah. Right, it looks not like what we want. Not at all. So that's incorrect, I guess. Let me try this maybe. No. I mean, we did everything correctly, right? Start from 0, 0. It starts from 0, 0 times. Ah, no, that's incorrect. 0, 0 times. Yeah, it's still gonna be 0, 0, right? Yeah, let me look at the formula again. So this is 0, and this is just t cubed, t cubed. This is going to be 3 times 1 minus t squared times t times p1x, and then the same with y. And then this is 3 times yeah, that's the exact formula I used. So it starts in the midpoint some way. Maybe ooh, that's interesting. Ah, 1 sec. Maybe I need to do... you know, kind of looks like something, I guess. What if we increase the sampling rate? Ah. Maybe. Do this. Is it actually giving back, like... negative values? No, it's not. Oh, I know. Ah, I'm dumb. Okay. So... the way that we have to graph this is... right, so x is correct. Y is going to have to be... height minus that. Yeah. No. So the higher y is, I want it to be flipped. Okay. So I want, if that is the coordinate in the Cartesian plane, yeah, no, this should make sense. Okay, let's do row 1. Ooh, it's all over the place. Yeah. Oh, my bad. Oh, yeah. It's way too far. My implementation is basically the exact same thing. I don't get why we're getting weird values. Yeah, we're getting out of bounds and stuff like that. What's up, Guga? So when we get past the half point is when we go over. When we get past 0.4. What do I need the waves for? I need the Bezier curve for my waves, bro. Check out my waves. What I need the Bezier curve for is to rotate these things not so linearly, but to sort of do it like that. If you want a visualization, basically, right now, I have a function that looks like this. And sorry, I have a function that looks like the blue one, and I want to make a function that looks like the yellow one. Not yellow, sorry, pink one. So if I go, boom, okay? That's what I want. And I want those things to flop around back and forth, those crates, those boxes, according to this curve. And I found out that this is a Bezier curve, and I'm implementing a Bezier curve, but it's not working. Yeah, exactly. To make the sea natural. But it turns out Bezier curves take way longer than I expected to implement. This was supposed to take me 30 minutes, and I've been doing this the entire stream. Well, it has taken me almost 2 hours. Yeah, slightly random, yeah. Freaking... Okay, I'm gonna bite the bullet. Not bite the bullet, but like... Write me a function that takes 4 arguments. Maybe I'll do some shader. Yeah, I'll do a few shaders maybe. The sea will need some shaders. Yeah, I can't just have a sprite. I'll probably need a texture, and I'll modify that texture based on the shader. Yeah. So check it out, it's gonna basically write the same function that I did. Oh, actually, I should change this function to say cubic. Now it's gonna copy the Wikipedia article, obviously. All right, tough guy, let's see what you got. Okay, so we start off with 0, 0. So AX is, it just optimized a bunch of stuff here. So minus, what kind of stupid? Wait, so if I do this, okay, bro. Okay, let me see. Ha! It works. Wow. Okay, so I don't understand some fundamental part of this thing, I guess. Oh, actually, these numbers are better. So we'll do like that. This is my Bezier curve. Right. So look at that. It works, but my function doesn't. Because I didn't understand this part. So like P3x minus P0x, so and then minus CX minus BX. That's not the cubic Bezier formula. So a plus t cubed you know what, actually because this has taken 2 hours, boom, we will learn Bezier curves at a later time. Right now we have to do some tasks. Right. Yeah, so let's do it according to the Bezier. These are not the control points, they're the starting and end points. Oh, actually, we can make this better. Now rewrite the function to only return the y value. Okay, we'll take this. Why did it need to actually do this? I don't know. Yeah, I can remove some stuff from here, but no need. Okay, so yeah. And this can be rewritten in terms of this. Yeah, you could do something like this. So local x is equal to Bezier t p1x p2x. So y is math Bezier t p1y p2y return xy. So if I use this in my test code in here, okay, let's do bloop like this, and Bezier 2D. Boom. Okay. I just simplified the function. Great, so that works. We'll do tests. Yeah, okay. Anyway, yeah. So we've got okay, so how long have we been going? This took 1 hour and 40 minutes instead of 30 minutes. This is terrible. Okay, so yeah. Actually, we don't even have this yet. No, we don't have this yet. We only have the Bezier function, right? So we're gonna do water and this is gonna be Bezier. That's it. This is just the only change we needed to do. If I had had a Bezier function, I would have just done this and it would have been done in like 20 minutes. But let's look at this here. Ooh. Yeah, that's too much. All right, let's divide this by like 4 or something. Ha! And it turns out that we didn't even need a function that's that harsh. Yeah. That's pretty bad. That's really bad. Oh no, this is useless now. Oh no, my bad. So actually this is incorrect. Okay, so I'll do yeah, so yeah, so what we need is Bezier lerp, so math lerp, and f1 to f2. The Bezier is going to be this, but 0.85, 0.05, something like this. Yeah. Math Bezier. So look at some of these boxes here. Okay, now we have that. So I'll just to compare, I'll do the previous version. Okay, so hold on. So this is the result of 2 hours of labor, basically. The one on the right is the old style. The one on the left is the new style. And if you look at them, I would say the one on the left looks much better. Not much better, but better. Yeah, so this is what yeah, so just look at one box. Like let's take the first one from the left, okay? You can see it moves to the left, then it sort of moves to the right, and it sort of shifts back. Okay, so yeah. And now look at the one on the left here, okay? So you can see it sort of, it's not as jarring, the movement. Let's look at a straighter one. By the way, yeah, okay, let's look at this one, the fourth one from the left. Yeah, okay. The one on the left is slightly better. It's only slightly better. Yeah. Oh well. The thing is, the previous one was almost good enough, and this one is just good enough, which is still a qualitative difference. So yeah, oh boy. So let's do 1 hour, 50 minutes. Yeah, commit, add local rotation noise. Oh boy. So that's done. That took like, I had 4 times more time. Wow. Let's make a boat. Okay. Let's make a frickin' boat. Okay. I'm gonna take the box and build off of that. So I'll do, yeah, that's default. How big do we want it? We want like 3 crates to fit on a single boat, I guess. So we'll do not 150, let's do 200 be the width. Height should be like 150 or something. Let's go to 230 even, yeah. Collider density, yeah, let's make it 5. Yeah, this looks okay. Then we go, yeah, this is unacceptable. We need physics, polygons. Except this is not actually good enough. Here's what we're gonna do. I'm gonna do collider polygon, I'm going to define this in terms of an array of points. So the first point, let's see. So I want a boat, right? And it needs to be like this. So to make a slightly believable boat, we can make a triangle. We can make a pretty steep triangle like this. I guess this could work, but I would rather have something like boop, bloop, boop, and then like this. The language is Lua. It looks like Python, and it's almost as easy as Python. But you have like these squiggly lines to determine both arrays and dictionaries. So we're gonna define a bunch of points here, right? So we want a boat that looks like this. So from the center, I guess this would be like minus 230. Yeah, I'm gonna actually need to draw this stuff. All right, so come on. There we go. There we go. Okay. So if the collider width is 230, this is going to be minus 230 divided by 2, right? And the y coordinate is going to be minus 150 divided by 2, right? This one is going to be just a positive version of that, and this one I'm assuming is going to be something slightly different, right? So yeah, didn't actually need this much effort to actually draw it. Anyway, so first point is actually I'll define the collider polygon outside like that, and this is going to be, let's see. So the first point is minus boat collider width divided by 2, as I said, and the y coordinate is going to be minus boat collider height divided by 2. Okay, top left. Then so this goes clockwise, right? So we go boom, 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 and boom. Okay, so this one is going to be the second one. It's going to be basically the positive side of that. Then we're going to have the bottom right. So I assume, so this is, if I were to make this, if I were to disassemble this, so this is basically like 60% of the way there, or maybe 50. Let's go with 50. So this is going to be 1/4, okay? The boat, we'll do it like this, boat collider width times 0.5. Yeah, no, I'll keep it this way. With half times 0.5. And the y coordinate is going to be boat collider height half. Yeah. Same goes for this one, except this is incorrect here. Okay, so let's do like this, and then like this, and we'll do this like that. Yeah, this looks cleaner. There we go. So, and then this is going to be minus this. and plus that. Okay, so that's the polygon. So when we add physics, what we want to do is not do this, do a different kind of thing. And we'll do Yo, that boat is way too big. The height is way too much. Oh, by the way, I need timestamps on this. So this, yeah, we started this 2 hours in. Okay, so it's been 12 minutes so far. Okay, so we'll do, yeah, collider height is way too much. Let's do 100. What was I thinking? What? Oh, this is 10. Still way too tall. Ooh, look at that. That looks like a boat. Eh? Oh no, the boat is capsized. Yeah, this is where my physics sucks. So I should have something like, I should give it torque. How would I find out the rotation of the object? body get rotation, something like that. We'll do it here. Maybe fixture. Get angle. Okay. Okay, so here's what I'm gonna do. The boat, okay, the boat looks pretty good. I would say it even can be not as tall. Okay, the boat looks pretty good. Here's what one thing I would add. Maybe it doesn't. These things don't need to be that steep. Okay. Ah, that looks pretty awesome. Oh no! The boat is capsized. It needs to be heavier. Yeah. Collider density needs to be like freaking. Ooh, yeah. If it is heavier, it's gonna sink. Yeah. Let me see. Boat. No, levels. Yeah, if it's heavy, it's gonna sink. Yeah. So it can't be that dense. It needs to be light, actually. Okay, so here's what I'm gonna do. If it's a boat, I'm gonna tell it to want to rotate towards its initial angle, okay? This is what we're gonna do. So, frame self body get angle. And I'm gonna, oops. So this is gonna be 0, okay. So I want to keep rotating it towards, okay, so we'll do anti-capsize. What do we name this? So basically we're gonna be, here's what I'm gonna be doing. Getting the angle. This rotation, okay? And then we're gonna be applying a counter force to that to get it to be 0, okay? So anti-cap torque is going to be minus R times self T-cap torque. We'll do anti-capsizing torque applied to object each frame to keep it from flipping over. Okay, this is gonna be, let's do let's do 1, and this is gonna be times self. Oh, actually, yeah, doesn't matter. Get mass or something like that. Okay, I want this to be sort of a square. Uh-oh. Yeah, that's wrong. Oof. That's rough, buddy. Right, so we've added, yeah, this needs work. Make capsizing. To I would say we made a boat. Yeah, I would call this a boat. So we'll go. So this took 31 minutes. Let's add camera controls. Okay. Add primitive boat. Let's add camera controls and then I'll call it a day for the stream because I gotta go. Yeah. Right. I will add a to-do here though. This is a good article. What is that music? Oh, it's coming from here. Why does this autoplay?
Back of that.
Right, let's add camera controls. I'm gonna copy a bunch of stuff from my other game. Okay, I just added camera controls, and that took to 19 minutes. Good job, me. Yeah, so the camera controls are in. Yeah. Ooh, my bad. There's one thing I gotta get right. Yeah. So. I love it when things just work the way you expect them to. Get back in here. You two, get back in here. Boom. All right. And the thing is, it's just way too heavy. I mean, way too light. When this crate hits this guy, like, maybe I should do... yeah, this capsizing needs to be fixed, but the boat also needs more fixes. Like when I put a crate on the box, on the thing, it shouldn't just sink like that. Yeah, it shouldn't just flip around like that. If this was really, really heavy, then it wouldn't flip around, I assume. Let me try that. So boat, let's do 300, and for water, let's do 1,000 or something. Okay. Oof. Okay. Maybe 300 is too much. Maybe like 100. Oops. No? Okay. Let's do 10. Yeah, okay, that's way too light. Uh, 60. I don't think so. Yeah. Oh, my bad. We'll do cursor. Yeah, that's not gonna cut it. Let's turn on waves and see how that plays out. Okay, I'm gonna say that's camera controls. Actually, yeah, that's camera controls. And I'm gonna call that a good stream, a good 3-hour stream. So yeah, current state of the game is, yeah, we've got buoyancy, varied buoyancy based on the weight. We've got waves, which play with the objects in the water, and they sway back and forth. And also we have a boat, which it's a pretty. We have camera controls as well, by the way. And this is a dysfunctional boat because it can't really serve as a boat. Look, it's gonna knock this thing over. Can't really like hold the things, you know what I'm saying? Maybe the boat needs to be bigger, you know, maybe, not sure. Maybe if we make it like 530 or something like this. So if we drop this, no, it still doesn't work. Maybe it needs to be like 100 or something. Yeah, maybe the boat needs to be really big. And then maybe if we drop this guy. Yeah. Guess we might have to implement some sort of better version of buoyancy, I guess. Yeah. Because right now these crates, like, they should be able to rest on this thing without it tipping over. But they can't, unfortunately. Maybe I should do forward and backward force as well on these objects. I mean, look at this. Even a slight force is gonna make it tip over. Maybe the collider angular damping needs to be like pretty high up there. Does that do anything? Just angular damping, okay. Yeah, okay, I guess this kind of works now. Yeah. But the anti-torque, yeah, this needs to be even higher, so... how many zeros is this? I've lost track. Oh, now this boat is working. Look at that. We just needed to tweak the values a bit. How many crates does it take to tip this guy over? Yo, we got a boat. I'm on a boat. I'm not sure what the hell happened there, but I think they all despawned because I'm dumb or something. Sometimes it doesn't work. Yeah, like what the hell happened here? There's still 4 objects, but it's like, what? Let's do it this way. Yeah, playing with lots of big numbers in Box 2D is... Why do they disappear? I have no idea. They just disappeared. Yeah, no, I think... Oh, okay. Okay. Maybe what if we do 10 on this? Will they still disappear? Let me see. This might be a camera bug. Oh! Yeah, this is a camera bug, I think. You know, this is so weird. Yeah, we have a camera bug as well. So we'll do so what was this value? It was like a bajillion. Let's do 40 and 200. How was that, right? And the density needs to be like 3. Look at all this stuff I'm balancing on it. And it's working. Kind of. Oh, it's not working now. This is terrible. Aha! So, why did this happen all of a sudden? Ah! This is in the wrong place. There we go. So that's what it was. That camera bug again. I'll adjust it later. But yeah, so far so good. Okay, that's it. So that's the state of the game. Yeah, we're gonna call it a day for today. Right? So I can put boxes on the thing without it capsizing. That's nice. Ah, it's sinking. Let's sink this ship, baby. Let's go. Oh no. Well, there you are. Okay, so that's it for today. This is probably the last stream on this game prototype that I'll do. And yeah, that'll be it. Maybe I'll do one more. But for now, that's it. See ya. Thanks for watching.